Mm-hmm. Okay. So let us continue with it. We have the differential equation, and our task is to solve it. But generally speaking, we are using computers, and computers works not in a continuous time but in discrete time, and this is why we need to discretize it. So, and instead of solving an equation that looks like this, that one means continuous time. Continuous time. We're going to deal. We deal with discrete. Discrete time system, and it's gonna look like xn plus 1 equals to fd xn plus not plus comma un, when d stands for the discrete. So instead of using x dot equation, we're gonna use xn plus n, when n is some kind of sequence, so the next sequence equal to some equation. Okay, so we need to discretize our initially continuous system, and in order to do this, we are going to use integrators, and any simulation package, any simulator use these integrators to do the discretization, and there's several of them. We'll cover few of them. So the basic one is called, so it looks like the following. So the basic, the most simplest discretization is looks like xn plus 1 equal to xn. It's like any one equals to the previous one plus h times fd xn un. So it is like a previous step plus some new step, and h is called time step, and fd is basically our function. So it's like we take a previous solution and we compute some step and we plus it, and we just do our iterations. It's something which is called forward Euler.
You mean FD, you mean F now, right? You mean the F of the continuous.
FD, it means discrete.
Yeah, but you wrote xn plus 1 is equal to FD, and xn plus 1 is equal to FD and other stuff. So
I didn't get it, your question.
I think it's just an example. I think you're talking about like that.
So this is in the general form. This stuff in general form, and that one is a specific way how we solve this. It's like in general, so the next step is some kind of function. And how do we compute? If we compute it like this, it's called forward Euler. So there is a name. So I do not do any derivation. So I just state as a matter of fact. I mean, I do not do derivation for two reasons, basically. We don't have any time for that. And I'm not the one who have to tell it to you because of, I mean, I do not have a lot of experience in that. It's not my piece of bread. I'm just explaining you the basic stuff. So we have a continuous equation, then we need to discretize it, and there is a bunch of different integrators, and the most simplest one is that one. And if you are interested in this, there is a course that I really recommend you about control from Carnegie Mellon University. It's something that I'm digging into right now. I mean, I would like to study more stuff, and this is something that I find out from this course. So I will give you the link for this course as the extra material, and right now I would like to make just a few emphases of something which is important for us. So this stuff is called forward Euler, and it is the simplest. Why it's the simplest? Because in order to compute it, you need just your equation. You need to know your previous stuff. You need your control and time stuff. So basically, that's it. But there's a significant, crucial problem with that. It's not stable. So in order to show you that, I'm gonna use this script. This script is not provided to you because it's not something which is done by myself. Basically, practice task from the course that I just mentioned, but just that been rewritten from Julia to Python, and it's been done by Kirill. So Kirill maybe on practice give you a little bit more details. So what I would like to show you here. So here it makes a simulation model of a pendulum. So it's pretty much the same, but just pendulum like this. There is here you can see an equation. Is it possible to make it bigger? I'm not sure. I do not want to waste time finding out how to make it, font bigger. Control plus, yeah, it works. Yes. Okay. So there is the equation, just like we have done it for the mass sprung damper. Then it's been written in a form that we try to do. The same stuff. So it's ugly, and there's something that we derive also was ugly. But still, and then you can just write an equation, small function that describe its dynamics. Look, so this equation, it is something which is here. Look, x dot is a vector of the velocity and acceleration, and here it returns an array of velocity and acceleration. Velocity is something that we provide inside, it is like a state, and acceleration is something that we compute using our model. So basically, this is our model. The acceleration equals to something that we had previously, the same stuff. So basically, the equation for the acceleration. So, and this equation can be, you can put it here, and you have a model. So this is this piece of script, a model of a pendulum. Now, what should we do? We need to discretize the continuous mechanics. So this equation is continuous, but we need to discretize it. So here there's a bunch of stuff that how we do discretization, and I encourage you to take a look at a few videos, not like today or tomorrow, after our part of the course, I believe. And the first simplest method is the forward Euler integration that I just.
I'm sorry for that. That's what I meant. The f in h time f, it's not the f discrete.
Yeah, you're right. You're right. Yes, yes. The whole stuff is the yeah. So here, yeah, like this, right? Yes, thank you. And here it's also a passive pendulum. This is why we don't have any U. It looks like this. And here you see how simple the step is. It's just xk, the previous step, plus time step, it's just a scalar, times something that is the input of your return function for your model. And then what is you do on a range of time. So there's a vector from 0 to some time of simulation, for example 10 seconds. And since you have discretization, you know how to split this vector on the pieces. And then you just compute the value for each of these time array. Is it clear? So let's take a look at the results. Here. Boom. Yeah, and you can see a plot of the velocity and acceleration, and you can see that it blows up. And it blows up because of the inherent behavior of the Euler, forward Euler system. If it doesn't have any damping there, it will just blow up. If you add damper there, and it's going to be your first practice actually to try with it, to play with it, to add the damper. So if you add damper, it's going to go to the rest, to the equilibrium point, but it depends on the discretization step. For example, H, so H is the final point here. For example, here the dot 0,1 is the discretization. I can make it smaller, and you see that it's much slower to compute. It doesn't blow up right now significantly, but still, if I'll increase time, for example, 50 seconds, you see how slow it is, and it's not precise. So it doesn't blow. It blows up, and you will see. You see, still eventually it blows up. It doesn't go into the rest position because of the. It doesn't have any damping. And this is why Euler is very easy to compute. So it's efficient to compute, but it's not precise. And for this reason, I told you that we're going to use Mojoko, and I go to the documentation of Mojoko, and here we will find out how does it do computation. So numerical integration, and you will see that the explicit Euler method and forward Euler, it is explicit. So the explicit Euler method is not supported by Mojoko. You know, because of its inherent behavior, it's not stable, and this is why it's not included to the Mojoko because it's not stable. But it is the fastest one. And this is why we have several kind of integrators. And the next in line is something which is called backward Euler. Yeah. Backward Euler. By the way, in the course that I mentioned, they go through all the points, and he describes why it's not stable. So he tells about stability and the eigenvalues and the real parts of eigenvalues. So he goes through all the details why it's not stable, how can you compute stable it or not. So, but still, I'm not going to give you all this information because it's not a point. It's not my point. It's you know, he took 4 lectures to describe this stuff. It's like 60% of our lecture. Once again, that my point is to show you the main, you know, points where you should to take a look at. You know, so there is a huge course of the how to do integration and solvers. Another course how to do the modeling, how to do control. So it's like you need to study this course, this, and this from this university, this university. So it's great that most of the university has their own courses like open, and I will make a few citations on this. Yeah. Since our lectures during last for the week, the whole semester, I encourage you to watch another courses from the whole, you know, the whole world. And as for us, we have just like we like a community, and I give you just a little background. Yeah. So let us continue that. Okay, extra comment. So forward error, it's something which is called explicit. In Russian, it means явный, explicit. There is explicit and implicit. Implicit, значит неявный. Explicit, that you know that in order to compute it, you need just a past state. Implicit, you need future stance. So you need some kind of prediction, and this is called implicit. So this is explicit Euler, which is called also forward Euler. There is also another method which is explicit, which is called Runge-Kutta. Have you heard about it? So Runge-Kutta, it's like an industry level. It's very precise, but it's also not cost efficient. So the idea is the following: that x n plus 1, so it's like the Runge-Kutta. It's also called RK4. 4 because it makes 4 steps to compute. Yeah, yeah. So in general form, xn plus 1 equal to fd. It depends on xn for the passive system. And in order to compute it, we need some coefficient k1, which is equal to f xn plus half of a time step, k1. Then we need to compute k2, f xn plus another half, k2, and k4, f xn plus h, k3. And finally, xn plus 1 equals to xn plus h times 6 k1 plus 2k2 plus 2k3 plus k4. So the idea actually that forward error, that the one that we had before, it utilized linear approximation. Look, if you have like a behavior like this, and it is like a state, no, time state, and in order to compute the next step, what you do, you just make a fix approximation which is linear. As for the Runge-Kutta, it fits not a linear but a cubic spline, and this is why it looks so nasty, but it's very precise. If we go to the example that we just had, by the way, for the forward error that we had before, so the main idea was that the real part of the eigenvalues, if you don't know what does it mean, you need to just check this information. The real part of the eigenvalues of your system must be less than 1 for the discrete system, and here you can see for the any h, it's more than 1. It decreases to 1, but it's never less than 1. And this is why it's inherently unstable. So if you add extra damping, it will be less than 1. But still you need to choose the proper discretization. And if you have hardware which is slow, and you cannot allow to yourself proper friction, how do you say, frequency. In this case, your system will just blow up if you use this forward error for your controller. Yes. So this is like the main idea. Why is that and the whole derivation? Please take a look at the course that I mentioned. It will be in the chat. I will add it. So basically Runge-Kutta, and here you can see so all the stuff that I just repeated at the iPad. Yes, there is K3. Yes. So it is K3, it is K2, and K1 is Fxn, like this. Now it must be correct. Yes. Yeah, now it's correct. Great, thank you. So basically we put it to the a method that describes our pendulum. So it's like a different, so the continuous dynamics is the same, but the step is different. So here I had this stuff, and instead of that we have this. The continuous dynamics is the same. Basically here it's the same idea, since it's explicit, and we can run it, and you can see that it's stable. And you see that h is just 0.1, so it's very small. It's computed more faster than the forward error with a small time step. So for the 50 seconds, you can see that it's stable.
So it is faster than forward or and
No, it's not faster. It depends on the age. If you make age small, you do a lot of calculation. And here it's faster because we have a small, I mean, not small, big time step. If you shrink it, it's gonna be slow.
Slower, yeah.
Much slower, because it makes 4 calculation instead of 1, because cubic polynomial.
Yeah.
But it's always precise, and it is like industry level. And you can use it. It's very great. And by the way, right now we're gonna use it, I believe. Okay, just let me finish with integrators, and then we go back to the mass spring damper. So it is explicit. Why it's explicit? Because it uses just the previous state, and it uses previous state, and it makes prediction what will be the second step. Forward Euler use linear approximation, and the Runge-Kutta uses a cubic approximation. There also exists something which is called implicit. The idea is pretty much the same, so I will copy stuff from here. But instead of xn, I'm gonna write n plus 1. So look, now it uses not a previous step, but a future step. Hmm?
Actually, it uses the same state. xn plus 1, xn plus 1.
Well, we are trying to predict xn plus 1.
So yes, so you can trying to compute xn plus 1, but in order to compute it, you need to know this in order to compute it. Look, in order to compute what is the value of xn plus 1, you need to know it. You see, and this is why it's called implicit. So basically, in general form, for the implicit stuff, we do the following: that function that depends on the future step, current step, and the current control equal to 0. So, and instead of what do we do here? We tell that fd that depends on this stuff equal to something that I have written. So for the passive structure, it will be just n plus 1 minus xn plus 1. So put it here, equal to 0. And now it's root finding problem. So you need to compute it as an equation. And this is why you have not only integrators, but also solvers. And solvers, they do compute this equation in order to find out what will be the x. There are several methods how to do root finding. There is something which is called fixed step, the simplest one, and you can also see a lot of information and the great course that I mentioned before. But also there is a method which is called Newton method, and let's just use it a little bit. So the idea is that for the discrete system, the fx plus delta x, like the new value of some function, will be its approximation. The previous value plus partial derivative times delta x. And that partial derivative is called Jacobian. And it maps change delta x to the delta f. So there is a vector space of delta x's, vector spaces of delta f's, and there is Jacobian matrix maps this stuff. Why it's so? So basically from the Taylor series, and this is two terms from the Taylor series, and you can go on and you can make something like the first term, the second term that I just wrote to you. You can add here an extra term, and it will look like this. Something like this. But we're gonna stick with the only two terms to make the system easier. So, and the Newton method basically it used this idea of approximation, and it basically set the approximation to zero. So according to the Newton method, we need to set approximation to 0, so such that fx plus delta x will be equal to 0. It means that this stuff has to be equal to 0. Let me just copy. Equal to 0. And from here you can compute delta x. What it will be? Just minus fx, and then you need to multiply it with the inverse. So minus delta f delta x inverse fx. Do you agree? So you compute delta x, and then what you do, x equal to the previous x plus delta x, and you repeat it until convergence. So you do iteration, and you need a few iterations to find out what will be the x. What will be f here? So here you can put the backward Euler, for example, the equation for the backward Euler, and it will look the following. So example. So for the backward Euler, so once again, backward Euler, it is integration, implicit integration. In order to solve backward Euler, you need to solve root finding problem, and in order to find root finding problem, we use Newton method. So our task is to minimize some function, and here to the function you can put basically any function. Here it will be the pendulum, the continuous dynamics of the pendulum. And according to the Newton's law, we need to use a partial derivative, and that partial derivative is happened to called a gradient, and it is denoted by the this triangle. Nabel, Nabel notation. So, in order to compute this, we need Newton law. Newton method, not the law, method. So, and it's supposed to be equal to 0, and then the gradient of function plus linear map of this gradient times delta x has to be equal to 0. And from here, just like I draw here, you need to compute what will be the delta x, and it will be minus this stuff delta fx. So it is a gradient. Here it's like a gradient of a gradient. It's also called a Hessian, or it is noted as a gradient in power of 2 fx. And here at the example, yes, it's like I skipped the fixed point because it's kind of simple, but it's not so precise as a Newton. So fixed point makes much more steps than a Newton. Newton makes 3 steps to compute it. So it's not the point of our discussion. The idea is that there is a explicit and there is implicit methods. Explicit that use previous state, implicit which is uses estimation of the future step. And how do we compute it? We compute it by optimization, and we do iteration until convergence. This is the idea. And if you take a look at the Mojoko, you will see that it has several of methods, which is called semi-explicit, implicit, and velocity, fast implicit. So it has 3 implicit methods with a little bit mamba jumbo. We'll take a look at later on, and Runge-Kutta, which is explicit. And explicit error is kind of forbidden. Okay. And finally, right now we can go to the material of our spring damper system. So this is the block that I just draw to you, and you can assemble a similar system at MATLAB Simscape. Or if we stick to the Python, we can do the following. So here I'm using not a Newton's law, Newton's method, but still it's backward error. You can see that it's do iterations until convergence. So epsilon e here is a like an epsilon is a tolerance, and so we do iteration. You can see here a while loop. It makes iteration until convergence, until we have a small error between I mean what we just compute. And here it is the result of our simulation. It is the position and velocity of a mass in a sprung damper system. And this is the equation that we derived previously. So where it was the ugly stuff here, and this ugly stuff is right here. You see, minus m divided by minus 1 divided by m times damping, gravity, spring force. This is the stuff. So 1 minus 1 divided by m, damping, gravity, spring force. And this is the x double dot, the acceleration. And since we need to return state vector, we need to put their velocity and acceleration. So it's x dot, right? So, there's beautiful x equal to the just beautiful x, it is position and velocity, right? And if you take a time derivative of this beautiful state, you will have velocity and acceleration. Remember, there was two different x's. The beautiful one, beautiful, let's call it nice, and ugly. The point is that this state time derivative of a state represents velocity and acceleration. This is the velocity, this is the acceleration, and it's something that you see here. And you can play with the different coefficients. For example, instead of backward Euler, you can try forward Euler. You can disable, for example, damping, and your system will blow up. If you add damping as it here, it's gonna work. It just depends on time step. So you can come up with some time step that works. Okay. Whew. I think it's a lot, right? Yeah. So let's make some a change in our activity. Kinda a play. Let's go completely to the different story, and let's come up with a list of advantages and disadvantages. So what we just done, we just understood what is a modeling, act of creating a model which derive a model for the mass Planck damper. We do understand what is a simulation. And simulation is just you do integration of your model. We know now that there is something which is called forward Euler, backward Euler, there is Runge-Kutta. We do understand what it does mean solver because of the implicit methods of integration. So we already know a lot. So there is a base of our knowledge. And we do know that depends on your result depends on your time step, it depends on your integration, that it's not like a beautiful picture that this simulation is just something easy that you just press the button and it works. It's controversial. It depends. You need to understand what you're doing. So let's just play a game and come up with lists of advantages and disadvantages. Why simulation is better than a real experiment, and why real experiment is better than a simulation. Advantages and disadvantages. So let us divide in groups, like 2-3 people. Okay, and work in pairs or in groups to come up with these lists, and just keep in mind that simulation is kind of controversial. It's not always positive, it's always sometimes negative. And what will be the advantages and disadvantages for the virtual and for the real experiments. Okay? So do this. So you divide in groups some kind. So you next to the, I don't know your names. So split in groups as you wish.
Professor, I have a question.
Yes.
Okay. So far you talked about simulations and modeling.
Yes.
On a fundamental scale, what exactly do we look at when we want to model a system? That's fundamentally, what are those factors we look at?
Your question is great. Let me answer this for the whole audience after the practice, right? Because it's kind of loud here.
All right.
Okay, and I will ask you to repeat the question. So guys, we can do the same stuff in the breakout rooms. So I will make a few breakout rooms such as you can discuss it. So I will make like 3 breakout room and I will assign automatically. Okay, so it will be 5 participants per room. So I open the rooms, you can go to the rooms and you can discuss it in your groups, okay? Let us continue with the results. So I will turn on my iPad and we'll write down the results. Mm-hmm. Mm-hmm. All right. So there is a list of advantages. And this advantages of simulation. So, and the disadvantages of simulation with respect to the real experiment. Okay, what do you have? Let's start.
We can't see the screen.
With the online, offline students, and then we'll proceed to the Zoom.
We just can't see the screen if you're going to show.
Fix it. Yes.
Yeah. Thank you.
Yeah. All right. So advantages and disadvantages. What are the advantages? Cheap. Simulation is cheap. Do you agree?
Well, sometimes it can be costly, but most of the time.
In general, no?
Yeah.
Zoom guys, do you agree?
Yeah. Yes. In most cases, it is cheaper.
All right. Let us proceed.
We have some real-life, but they tend to sleep in their simulation.
Errors in real life?
Errors caused by human factor.
Human factor. Okay. What else except of human factor? Is something else? Except of you. I mean, what do you mean? You mean human factor or something else? Human factor. So sim doesn't have human factor. Do you agree? You don't agree.
Well,
Let's have a discussion before. So the star means that you don't agree. I mean, this is my star. Okay. Let us move on.
Simulation, we can conduct a more controlled experiment, like
More controlled. So it's the same. The experiment is more controlled.
yeah,
Mhm.
create an environment that sometimes we cannot create in real life,
Mm-hmm.
or we can measure a sequence that it's very hard to measure in real life.
All right. More controlled.
Is it talking about safety or the constant I mean,
Could you repeat?
is it talking about the safety or a constant control? Yeah.
Example, like let's say we have a system, we have a wheel for snow, and we are developing it in summer. So we have to wait 3 or 4 months until the winter is coming, then we can test it in real life. But we gotta get an environment and we simulate it and we can test it.
Yeah. I will just repeat, guys, to the Zoom. I will start from the beginning. So, all right, it is already written. So about the virtual experiment is more controlled. That in the virtual reality, you will see how everything is interconnected, and you see how different subsystem influence another subsystem, right? It's something that you would like to express. Something like this. Okay, let us move on.
You can easily modify parameters.
Modify. Okay, what else? Anything else? Do you have a on the list?
it can be quicker to set up a simulation that is to construct a real life experiment.
Mm-hmm. Mm-hmm.
I don't know. So it depends on the experiment. Well, yeah. Simulation is well.
Maybe it's also safer for
Safe. Mm-hmm.
Sorry, can you define simulation before? Faster to create than the real experiment. Okay. Yes, yes. It also not always cheaper. It's always cheaper.
Sometimes the scenarios that we cannot create in real life, like for example, we have a controller and it's looking at the system in unstable condition, and this unstable condition might cause damage like to mechanical joints or different circuits. So
How do you spell it?
they say that real life experiment sometimes can damage the system.
Real one. I mean, it's you'll go right on the safer. Is it the 6?
The simulation allows the stress testing.
Yeah.
It's like you can repeat as many. Yes. So sim, you can do as many iteration as you want.
Okay. Also, you can do prediction
of lifetime and other parameters, which in real life
Which is measurable in lifetime, but it takes time.
it's easy to test our system in a different environment, like rough terrain or a snowy terrain in simulation.
Could you repeat it?
It's easy to test our system, physical system, simulated system in different and a challenging environment. It's easy to, yeah.
Easier to simulate in challenging environment.
Yeah.
I think, okay, no, let me write. Easy. Number 3 is more controlled. Yeah, maybe you're correct. That let me just put in parentheses. Challenging environment. Are included. Something else? Specific? Guys in Zoom, do you have something to add?
Found a lot of experiments by changing parameters.
Did you finish changing parameters?
Yeah.
I mean, here, so the virtual experiment is more controlled. We mean that we can change any parameters and we see how everything is interconnected.
So point number 4, yeah.
Modify parameters. So
I think on the line of 7, like you can do as many iterations. Also, like we expand this from time to space, we can do as many, I don't know, instances. We can deploy many instances to be trained at the same time, especially for RL. Like we can have a bunch of robots being trained together.
So he's talking about scalability.
Yep, scalability, exactly. Thank you.
Yeah, great. Some else specific one? We don't have any left time. We don't have a lot of time. Let's proceed with the disadvantages. Why simulation is bad?
Almost the opposite.
That real life is more expensive than sim. No, it's not. A disadvantage is not of real time. It's disadvantages of simulator.
Sim to real transfer. ISO.
Sim to real transfer, right?
Yeah.
Dependent on software.
Could you repeat?
Dependent on software.
Software is an issue.
Coordinates are expensive. So probably you have to buy
data is expensive.
Sorry.
Data is expensive. Computation is
Yes. So probably you have to buy one. So hardware is also an issue.
Computation is expensive. And see if what do you mean by hardware?
Well, computation.
Yeah, you need a hardware to do simulation.
Sometimes it's hard to model every uncertainty in real life, so it makes your model not very good for your application.
It's like not precise model.
Yeah, exactly.
I mean that model is always a model. Model, not reality.
Lack of physical feedback.
Once again,
Lack of physical feedback.
I understood the word feedback.
Lack of physical feedback.
I'm sorry, still I didn't get it. You can write in the chat. Lack of physical feedback. Is it disadvantages of a sim? I'm not sure that is disadvantages of sim. Okay, so we don't have any times left, and let us continue this table tomorrow, and we will discuss it. So we'll start our day tomorrow with a discussion: is it true or not, and so on. So thank you for your attention, guys, and that's it for the day. See you.
Thank you.
Thank you.
See you.
Bye bye.
Thank you.
Bye.